All right, so we're going to talk about ionic bonding here. But before we talk about ionic bonding, we should know that metals, since they're on the left side of the periodic table, have a lower electronegativity. They have less control over their bonding electrons, so they tend to lose those electrons, creating a positive ion. A positive ion, by the way, is called a cation. And then nonmetals have a higher electronegativity. Nonmetals are to the right of the staircase, so they gain electrons, creating a negative ion. Negative ion is an anion. So we're going to talk about bonding slightly, and there are three types of bonding: ionic, covalent, and metallic. Ionic is always between a metal and a nonmetal. So the metal loses the electron, and the nonmetal picks up that electron. Covalent is always between nonmetals, and then metallic, as you might imagine, is between metals. And so today we're going to talk about ionic bonding, which specifically talks about the losing and gaining of electrons between metals and nonmetals. So what's an ion? Ion is a atom with a charge because it's lost or gained electrons. A positive ion is called a cation. So most metals will become a cation. Most nonmetals become an anion because they gain electrons. Why do they gain or lose electrons? Well, they need stability. And stability is 8 valence electrons. So noble gases who have 8 valence electrons, or 2 for helium, which is considered full, they don't react. They're pretty stable because they have a full energy level. Why do noble gases have no why do noble gases have they don't have any electronegativity? The reason is electronegativity is measured as the control over bonding electrons. So we measure electronegativity when two atoms are bonding. Because noble gases do not bond, we never measure the electronegativity. So there's no electronegativity because there's no bonding for those group 18 or noble gases. Let's talk about ionic bonding. So here we have a sodium, and if you remember the electron dot diagram, sodium is in group 1, so it has only 1 valence electrons. And then let's say we take chlorine. Chlorine's a halogen, group 17, it has 7 valence electrons. So if you remember going through these electron dot diagrams, what you'll see is that sodium has low electronegativity. It wants to get rid of that 1 electron. Getting rid of that 1 electron will actually eliminate a shell, a valence shell, which will give it a full energy level. And this chlorine, if it just needs 1 more to get to 8. And so they're a natural kind of fit. So this sodium becomes a +1. When it loses an electron, this chlorine becomes a -1. These charges actually attract each other, so they come together, NaCl. So NaCl is the formula, and then the name is sodium chloride. So notice IDE. So this is sodium with chlorine. To show that a bond has occurred, we actually change the ending to an IDE, and that tells us that a bond has occurred. Another example, say magnesium. And let's see, fluorine. So magnesium, if you look, is an alkaline earth metal, 2 valence electrons. Fluorine has 7. It's a halogen. So this magnesium ideally wants to get rid of these 2 electrons, and fluorine wants to get to 8. But fluorine can only take 1 of the electrons. So another fluorine comes along and is able to take the second. Able to take the second one, so then you get magnesium, 1 magnesium for every 2 fluorines. And as you add 1 electron to that fluorine, it makes a -1 charge. So for every, they attract, these are opposite charges, so for every 1 magnesium you have 2 fluorines. So you want to put that subscript of 2, that shows that there's 2 fluorines. And this is magnesium fluoride. One of the more difficult ones would be, for example, say like aluminum with oxygen. So aluminum, let me do it this way, has 3 valence electrons, oxygen has 6. So aluminum can give up this here, this here. So that makes it stable, but aluminum actually has 1 more valence electron it needs to get rid of, so another oxygen comes in. So, and then unfortunately that leaves another oxygen unhappy, so another aluminum. Because you see this oxygen here is actually missing. So we bring in another electron, making this aluminum not stable. It has 2 valence electrons. And so these 2 electrons go here and here. And so you get 3 aluminums, 2 aluminums and 3 oxygens. So this would ultimately come together, make Al2O3, which is aluminum oxide. All right. So this is kind of one of the harder ones that we can give you. There is something, though, that I do want you to be able to do. So instead of drawing all these electrons, which it kind of just takes up a little bit of time, ideally what I would like you to be able to do is if I give you aluminum, you know aluminum has 3 valence electrons. So it's going to be, it wants to remove those 3 electrons, has low electronegativity, so it has a +3 charge. That's, Al plus 3 is the most stable form of aluminum, the most stable ion of aluminum, because it removes those 3 and it creates a full shell. Oxygen has 6 valence electrons, so it's going to be a -2. It needs 2 more electrons. Oops. It needs 2 more electrons to become stable at 8. And what you'll notice is when you put them together, they neutralize. So right now there's a +3 charge and a -2 charge, right? So if we were to put these together at a 1-to-1 ratio, it would be an overall +1 because there's an extra plus charge compared to the negative charge. So if I add another oxygen, now what I have is a -4 over here to a +3. It's still not equal or neutralized. So I'll add another, but I can only add in increments of +3, right? Because I can only add more aluminum. So this becomes +6. Add another -2, and this becomes a -6. So now I've neutralized it, right? So for every 2 aluminum, I have 3 oxygen. And so ultimately we want to get to this, being able to do it a little more quickly.